start this one. All right, so where were we last time? Yeah, we sort of finished with, for the moment, the representation theory of the Poincare group, and I just wanted to have a brief discussion about relativistic kinematics, also just so that you get more and more familiar with the with the particles in the standard model. Here we were discussing conservation of energy and momentum, which is expressed through this equation. And we were, just to be concrete, looking at decays of the W boson. And more complicated decays, such as Topcock decays. The Higgs boson, I wanted to mention the Higgs boson decay to 2 photons because that was what was actually measured first, at least that was the first way that the Higgs boson was discovered around 10 years ago. And then I promised some exercises. So exercise 1 is to consider W boson decays. And we want to consider a W boson in its rest frame, decaying to a positron and neutrino. And then if you're given the energy of the positron, the first thing to do is determine the magnitude of the momentum of the positron. And then assuming that the neutrino is massless, try to calculate the energy of the neutrino. And for this, you can use the what's called the PDG, which is the particle data group. This is a sort of publicly shared resource for particle physics, which keeps a track of the properties of all known particles. So you can use that for the particle masses. And for these questions, you don't have to write down the masses to like 10 digits or something, or to whatever the precision is, you know, like 2 decimal places should be sufficient, 2 or 3. And then for the Higgs boson decay, if you're given the 3 momenta of the 2 photons, I want you to determine the energy and the momentum of the Higgs boson. Just to say that, just to finish this part, it's not only decays that where Lorentz invariance is important. You know, one can have processes in which you have many particles in the initial state. Then there's some sort of complicated set of interactions, and you could have a whole number of particles in the final state. And you know, every particle will have its own 4 vector. So let me suppress the Lorentz label just because to save time. So this would be particle 1. Let me do it in the forward way. P initial 1, P initial 2, etc. Some n particle initial state So you're supposed to think of these, and really, ideally, we think of these as coming in from infinity, where they are like free particles. They come into a region of space where they're able to interact with each other with a non-zero probability, and then some other set of particles. So these particles could all be different, by the way. There could be different types of particles as well. I haven't said what type of particle they are. And then obviously you'll have some final state particles, and they will have their own four vectors, and there could be m of these and n of the initial state ones. And then obviously what Lorentz invariant says about this situation is that the sum of the initial state particle four vectors is equal to the sum of the final state four vectors. Because that's the total energy and momentum of the initial state and final state, respectively. And so this equation is used a lot to discuss processes like, and these are processes that you're going to actually calculate in the types of processes that you will sort of be calculating the amplitudes for and the cross sections for. So the language used for decays is that you calculate the decay probability, or decay width, it's called. For these type of processes, you calculate the cross section, which is related to the fact that the thing you calculate actually has units of area, and you can interpret it as the area, the cross-sectional area through which the interaction takes place. But anyway, you know, you might have a process in which electron and a positron, or a muon and an anti-muon interact, and by exchanging a photon, then produce, for example, mu plus, mu minus. So in this case, this will be this is a 2-to-2 scattering process, and one uses, you know, as part of the calculation of the cross section, one uses Lorentz invariance to reduce the number of variables which enter into the calculation. So because in an experiment, for example, at the Large Electron-Positron Collider, one is colliding electrons and positrons, and if the accelerator technology is good enough, one knows what the initial electron energies and momenta are, and that's something that you set up the initial state by dialing the by changing the magnetic fields, for example, the power of the magnetic fields in the accelerator. So the question there is then, so in that setup, we know the initial state, electron energy and momentum, and positron energy and momentum. And then one wants to use the standard model to calculate the probability of producing, say, in this case, a muon and an anti-muon, but it could, one was also looking for the Higgs boson at LEP. So whatever the final state one is interested in, one uses the standard model to calculate the probability given say 10 million E plus E minus scattering events. What is the probability? How many mu plus mu minus pairs will I produce with a given energy and momentum distribution, for example? That's the kind of thing one calculates and then tries to compare with actual measurements, just to give you an idea of how the theory interacts with the experiment and what it is about the theory that we need to be able to calculate in order to compare with the real world. Okay, so that ends my little interlude on scattering and relativistic decays and kinematics and so on. I gave you there a couple of exercises to look at. Does anyone have any questions at all about this part? Because we're going to go on to fields next. Okay, so let's do that. So yeah, so now we're going to go on to introduce fields, and roughly we'll do it in this kind of order, but it's not actually going to be exactly ordered like this. First of all, we'll start by talking about why we use fields. Why, for example, why we consider quantum field theory. That will be very general without any mathematics. And then we'll start talking about relativistic wave equations and relativistic field equations, and then introduce Lagrangian field theory, and also then we'll go on to discuss symmetries in field theories. Good. So, like, historically, we sort of the field of physics jumped from quantum mechanics to quantum field theory at some point, and that was pretty. It was like almost 100 years ago. Now, why did we make that jump? Why did we stop using just quantum mechanics itself to describe particles? So quantum mechanics and wave functions. Well, the point is that quantum mechanics is really based on finite numbers of particles and, say, maybe more importantly, single particle states. As soon as it was understood that the world is relativistic, meaning that the world has Lorentz symmetry, the equation E equals mc squared means that the combination of relativity and quantum mechanics can lead to pair creation of particle antiparticles from the vacuum. I mean, even though that is a rare process, since quantum mechanics is all about probabilities, there is some non-zero probability that it will happen. And so the point is that multi-particle states can, and they will, appear. I mean, in this sense, I mean, for example, there's a correction to this diagram where I replaced the photon in the middle by a positron-antipositron loop, or electron-positron loop. And you see, if I cut this in the middle, we have this two-particle state, which is a virtual two-particle state, virtual in the sense that it doesn't even have to satisfy the relativistic energy-momentum relation. Only the final state particles have to satisfy those, but the multi-particle state does appear, and you can make this diagram much more complicated by considering higher order corrections. So, and they're virtual because of the uncertainty principle. So if you consider a short enough interval of time, you can get a large correction to the energy of a state, and that allows you to create these multi-particle states. Causality is another issue. Quantum mechanics, because it's manifestly, ordinary quantum mechanics, based on the Schrodinger equation, for example, will allow propagation outside of the light cone. That's obvious because ordinary quantum mechanics doesn't have relativity built into it. But even if you look at relativistic quantum mechanics, the same is true there, and it's for the same reason that these multi-particle states can appear. This is actually solved very elegantly by quantum field theory, as you'll learn in the QFT course or QED course. The other thing that we will talk about today is that relativistic quantum mechanics predicts negative energy states. We'll see how this problem is sort of solved by field theory as well. Another reason for thinking about fields is that fields, even before quantum mechanics, physicists were working with fields, mainly the electromagnetic field, because of Maxwell's equations. So the fact that quantum mechanics came along meant that we would need a quantum theory of electromagnetism, and that theory would presumably require fields, because the classical theory of electromagnetism has fields in it. So all of these, so there's many reasons for introducing fields. The reasons are sort of have different peculiarities to them in some sense, or different qualities to them. Okay, so we're going to begin with relativistic wave equations. So if we just think about the Schrodinger equation, one way to think about it is that it's simply the operator version of the non-relativistic, the classical energy momentum relation, E equals P squared over 2m. So, because if I take the differential operator representations for E and P, then E is just the square root of -1 times d by dt, or in our shorthand notation d0. Call this partial d0, and the momentum is minus the square root of -1 partial I. So if we turn that into an operator equation and it's acting on some function of x and t, then we get the free Schrodinger equation. So free meaning that we haven't introduced a potential, but then the potential just is a correction to the energy and will enter in the same way that the energy term is entering. We can just shift the energy term. So given that that works so nicely, we can simply take the relativistic energy momentum relation and do the same operation, and we'll end up with a relativistic wave equation. So we start with our relativistic wave equation, where I'm now, remember, set C and H bar is always equal to 1. So E squared equals m squared plus the magnitude of momentum squared. So if we just make the substitutions, E squared becomes d by dt squared, acting on a function phi, I'm going to call it. M squared is just m squared, and then mod p squared becomes minus partial I squared, so here meaning that we're summing over I. Remember, sometimes this is written as grad I squared or divergence squared. That's the notational point. So if we rearrange the equation, we can write it this way, or if we bring the derivative terms to the other side, we can write it this way and put the 0. So this operator here, we can now write in covariant form. And it's just given by partial mu upper, partial mu lower. And that plus m squared has to, when acting on phi, we should get 0. Okay, so what this equation is the operator version of the relativistic energy momentum relation. This equation is usually called the Klein-Gordon equation, although it's maybe not. Yeah, I want to comment on the history of it. I expect you to be able to make this derivation. It is straightforward, but sometimes one can get mistakes with signs and so on. So please try and go through this in your study time. So the first thing I want to do is look at the solutions of this, some solutions of this equation. So the claim is that there are solutions which I'll call phi superscript free, because these are going to have the interpretation of describing particles, free particles with some given energy and momentum. So the claim is that up to an overall constant, e to the minus I p dot x is a solution of the Klein-Gordon equation if p squared equals m squared in the relativistic sense. So let's check this. Maybe we do this. Let me do this on a slide here. So we've got phi is n e to the minus I p mu x mu, and we want to show that this function satisfies the Klein-Gordon equation. The Klein-Gordon equation is so that means we've got to calculate this combination of derivatives. So let's calculate d mu of phi free. So who's going to volunteer the answer to this one? How do I differentiate this with respect to x mu?
Minus I times n times e to the power times p mu times e to the power of minus I p mu x mu.
Thank you. So this is what we actually get. Which I can write as I can write it this way. And that means that when I take, now I need to also calculate this. I want to now calculate d mu of the result. And I already know what this is from the previous line, and that is going to be p mu with a lower index. Times, sorry, this is a mistake. I've forgotten them, minus I. And that's the expected result because d mu, the operator in the equation, is minus p squared, because d mu is I times p mu as an operator. And so what this shows is that phi free is an eigenstate of, I mean, classically, let's say, is an eigenvector of d mu with eigenvalue minus p mu squared, which is minus m squared phi free, and therefore satisfies the equation, because then this term cancels with this term. So this is why this type of solution is part of the reason why this solution is considered to be a free particle solution. So it describes a particle of mass m with energy E and, so with arbitrary energy E and arbitrary momentum P, apart from the satisfying the mass shell condition. Now, there is a problem with this equation in terms of looking at these solutions. You see that you can ask actually what, more precisely, what is the energy of the particle? Or what's the interpretation of the energy? And the problem is that all we know is that E squared is P squared plus M squared. So when you calculate E, there are actually two solutions, one which has positive energy and one which has negative energy. So the problem with this equation is that it has negative energy solutions, or at least this was thought to be a problem. And that was part of the motivation for Dirac developing the Dirac equation. But even the Dirac equation has the same problem. But as we'll see shortly, the problem gets resolved in a natural way because of the existence of antiparticles. So in the end, we can interpret the solutions in terms of positive energy particles and antiparticles. All right. Now let us look at this equation again. If I take the equation, which is I've written again in the top left there, and in the top right I've written the complex conjugate equation, because in general we want to think of these fields as complex. Then I can take the original equation and multiply it by phi star and minus the square root of -1. And I can take the complex conjugate equation and multiply it by minus I times phi. And if I subtract the second line from the first line, I end up with the following identity. Which you can convince yourselves of. Now, what that means is that there's an object, a 4 vector J mu, whose divergence, so put this as a check, whose covariant divergence is 0. And the components of this 4 vector are the time component is this quantity here involving the time derivatives, which I'll call rho. And the 3 vector components involve the spatial derivatives. So we can think of this as a conservation law, because because the time derivative, what this equation tells you is that the time derivative of rho is equal to the spatial divergence of J. So rho dot equals divergence of J. And then if you integrate over all of space, the divergence theorem will tell you that the integral of rho over all of space is conserved. So it leads to a conservation law. Rho we can interpret as a density of particles, and J we can identify as a current or a flux density, if you like. The same thing, it's just two different words to describe the same thing. So let's compute these things for our free particle solution. So that just means, so this is something also as an exercise. Just take the free particle solution that we just wrote down and calculate this quantity. And calculate the components of J mu using this formula at the bottom. So we see that rho is proportional to the energy and J is proportional to the 3 momentum. And then n itself is just a normalization constant, which I'm not going to specify for now. So J mu is proportional to the 4 momentum with coefficient 2 in this case. Now, if rho is interpreted as a density, like a probability density of finding these 5 particles, then the integral of rho over a spatial region, a spatial volume, should actually be a Lorentz invariant quantity, because it would just be the number of particles, let's say. And that is in fact true, so that fits with this interpretation that we want to give it. Because a volume, if you remember when we talked about length contractions under boosts, the same is true of any volume. A volume will undergo a length contraction under a boost. But the combination of rho and d3x is invariant because rho is the time component of a 4 vector. So that's nice. However, we still have this problem about negative energy solutions. The negative energy solutions would formally have negative particle number, or negative probability, if you like. It doesn't make any sense. So the way that this problem got resolved eventually is to include the charge. So imagine that we were, when this was being discussed, the only matter particles that were being understood were electrons, which had electric charge. And so if we imagine that this field is describing electrons, the idea is to multiply this 4 current by the charge. So more generally, if this is a more general type of charge, we'll call this charge Q as opposed to the electron charge E. Okay, so then rho would then, okay, I dropped this factor of 2, but it's not important. Rho would be Q times the energy times the normalization constant. So in order for rho to remain positive, we would then require that the negative energy solutions would correspond to negatively charged particles, and vice versa. So the point is that having positively charged and negatively charged particles present would solve the problem. And if we call the positively charged particles particles and the negatively charged particles antiparticles, then the point is that antiparticles solve this problem. So this was done by
Professor?
yeah, is there a question?
Yeah. In the sense, Q mentioned Q is about the charge of the particle. So for electrons, Q is negative and the energy is positive.
Yeah. I mean, it's up to you to say that the charge of electrons is negative. That's just something we define.
Oh.
That's a convention that we take. But what we call I could relabel, I could define Q to be minus E if you want. Without changing any physics.
Okay, but if the particle that I am talking about is positive, it would make the same diagram. I mean, consider an up quark.
Yeah.
It would be a positive charge and a positive. Yeah. Whether I fix the sign of the J as positive or negative for the solutions to make sense, I need the Q and E to give always a positive sign.
Yeah, that's right. We'll wait a few minutes, Mohammed.
Okay.
Sorry, I have a question also. Why you have my why you say the integral of rho over the volume should give us the number of particles?
Because rho is like the probability density in quantum mechanics. So this would be,
okay,
rho would be like psi bar psi in quantum mechanics.
We expect that because the analogy between the quantum mechanics, yes?
Yeah, I guess that's one way of thinking of it. I mean, it's a conserved. Yeah, I mean, exactly. You could motivate that definitely from the analogy of quantum mechanics. If I did exactly this set of where is it? If I did these operations on this slide for the Schrodinger equation, I would get rho is equal to psi bar psi.
I think if we depart from quantum mechanics and if we start with this theory, is there any reasoning that lead us to think it should be positive, this quantity should be positive?
It's a conserved quantity that in the non-relativistic limit becomes the probability density of quantum mechanics. So it has to be positive. But anyway, we'll see later why. I mean, we'll give a more fundamental formulation of this later.
Thank you.
You can see that for the free particle solutions, so anyway, let's look at the the case that was mentioned in the question for electrons. So let's consider J mu for the electron. So this would be given by -2 times the electric charge times the 4 vector of the electron. Positrons, on the other hand, would have plus 2 times the electron charge times their 4 vector. But you see that this quantity is also minus twice the electron charge times a 4 vector with minus E and going in the opposite direction. So mathematically, if I say if I consider the drawing the time axes as going from south to north on the blackboard here, then a positron going forwards in time with positive energy is mathematically is the same as an electron with negative energy going backwards in time. So that is actually the resolution of the puzzle, that the negative energy electrons solutions can actually be interpreted as positive energy positrons. Okay. Which means that relativity forces upon you antiparticles. So you can't just have a theory of purely electrons. You have to introduce positrons as well. And that's what Dirac eventually did. And that's what he got his Nobel Prize for, actually. All right, this is what I was saying before about the conservation of charge, but I see the time has come to, like, we've done 50 minutes. So let's take 10 minutes break and come back at, in, let's say 9 minutes. If that's okay. So on the hour, according to my clock here. Okay, let's resume. Yeah, so this the fact that the divergence of J mu is 0 means that the time derivative of rho is the divergence of J, which then, if we integrate this over all space, we learn that if the fields are such that the current J vanishes at infinity, this will be 0 by the divergence theorem, which means that the integral of over all space of rho will be constant in time. And that's an example of a conservation law. And we'll later learn that this is a consequence of a symmetry. So before I go on to discuss that, I just wanted to go back to say just a few words about just to sort of prepare the road for the quantum field theory interpretation that you'll get in the coming courses. So we have all of these solutions, so describing particles of a given, we have some fixed mass, and then we have all these different solutions for any four momenta which satisfy this p squared equals m squared relativistic energy momentum relation. In the quantum theory, the field phi will be promoted to an operator, and the different solutions, if we then, for example, do a Fourier decomposition of phi and then promote phi to an operator, then the coefficients of that Fourier expansion get promoted to operators, and what you find out is that those coefficients are like the A and A dagger of the simple harmonic oscillator, but now there's an infinite number of them. So when you quantize fields, what you're doing is what you give the interpretation of a quantum field as an infinite collection of simple harmonic oscillators. So a field, so when you go from quantum mechanics to quantum fields, you're going from a finite number of particles to an infinite number of particles. Okay, so where were we? Okay, so now we're going to introduce what's called the Lagrangian formulation of field theory, or we're going to apply it here to the Klein-Gordon equation. So to motivate that, in classical mechanics, in the Lagrangian formulation of classical mechanics, one starts with the action, and the action is the time integral of the Lagrangian. And the Lagrangian is a function whose values give you the difference between the kinetic energy and the potential energy as functions of the variables in classical mechanics, which will be the positions of the particles and their time derivatives. In Lorentz invariant field theories, one formulates a similar, one sort of generalizes this now to go from particles to fields. And because of Lorentz invariance, one considers the integral over space and time of an action, S. So it's the integral over dt and d3x of a Lagrangian density. And that Lagrangian density will be a function of the fields, which is the sort of analog of the particle positions, and their derivatives. But now, because it's going to be Lorentz invariant, we don't just, the time derivative is not singled out. We consider the d mu of phi as replacing, say, x dot. So the Lagrangian density is a function of phi, of both phi and d mu phi. So phi and d mu phi are to be considered as independent variables of this Lagrangian density functional. So if we now consider an arbitrary variation of the action, and we extremizing the action means that we want this variation to be 0 in the end, that tells us that the integral of the variation of the Lagrangian is 0. And if we work out what delta L is, well, we just apply the rules of, say, functional differentiation. Since our variables are phi and d mu phi, we'll get a term which is the variation of L with respect to phi. So we'll get the, which is the same as the partial derivative of L with respect to phi times this arbitrary variation of the field, which I'll call delta phi. But then we'll also get a term which corresponds to the variation with respect to the other variables, which are the d mu phi's. Sorry, this is, I have to correct this, sorry. So the second term, we just consider L as a function of d mu phi and differentiate it with respect to d mu phi. And then we get this expression here. And I need to correct the bottom here. Now, this second term, I can write it as, so I've skipped a line here. So if you compute d mu of the thing in brackets here, you'll get two terms, one of which is this one, and one of which is the, sorry, is what am I doing here? So if I do the next, I mean, yeah, maybe I should just fill in the gap here. Let me remove these integral signs because I'm just in the way at the moment. So if I look at this quantity, these two terms are exactly what we have coming from here. And this term is exactly this term, and the difference gives you this term over here. So in the end, sorry, this is, I apologize, but this slide is very messy. I was a bit sloppy when I wrote it. Okay, so now what we have is that if the variations of the fields are such that we always have suitable decay at infinity, because physically, we're always considering situations in which there's no physics happening at infinity. We're thinking of the particles as all being free at infinity. Then we have this total derivative term that we're left with at the end, which means that setting delta S to 0, this term has to equal this term, and that is called those equations for any field phi are called the Euler-Lagrange equations. Okay, so here I was just assuming that there's a single phi, but for most applications, the Lagrangian will contain lots of fields with many, fields with indices and multiplicities and so on. We can apply this equation for every individual field that's in the Lagrangian. And that's what we're going to be doing as we look at more and more complicated examples. Now, the Klein-Gordon equation, which is our relativistic wave equation, arises as the Euler-Lagrange equation of a specific Lagrangian, which is this one here. So this is our first example of a field theory Lagrangian. So it depends quadratically on d mu phi. This is, just think of it as d mu phi all squared. That is the field theory generalization of, x dot squared, which would be the kinetic, which would be proportional to the kinetic term, kinetic energy of a particle. So the first term in the Lagrangian is the so-called kinetic term for the field. And the second term, which clearly has the mass parameter in it, is the mass term, and this would correspond to a potential term. So the potential term, which is minus the term that appears in the Lagrangian. The potential for this Klein-Gordon field is a half m squared phi squared. So an exercise here would be to calculate the two quantities that appear in the Klein-Gordon Lagrangian. Well, basically calculate the Euler-Lagrange equations and show that the Euler-Lagrange equations for this Lagrangian are exactly gives exactly the Klein-Gordon equation that we started with. Now, the point about this L is that if you look at it, it's a Lorentz scalar, even though it has this, depends on phi, and it depends on the derivatives of phi, as we said. But because the Lorentz labels which appear are all contracted, we have Lorentz invariant Lagrangian, and a Lorentz invariant Lagrangian for fields guarantees that the equations of motion are also relativistic. And so for particle solutions, E squared will always be equal to P squared plus M squared. And that's going to be true for the many other Lagrangians, Lorentz invariant Lagrangians that you're going to encounter. Some of them you'll encounter here and others in the other courses. So what we're going to do now is look at the relationship between, so now we're going to consider symmetries in Lagrangian field theories. We're going to give it our first look. We're going to continue looking at it next week as well. The relationship between symmetries in field theory and Noether's theorem, which is the theorem that for every symmetry of a Lagrangian field theory, every global symmetry of a Lagrangian field theory, there's a corresponding conserved quantity. So when we derived the Euler-Lagrange equations, we dropped this total divergence term. And the point about that is simply that if you shift a Lagrangian by a total divergence and assume suitable behavior of the fields as you go outside of as you go far away from the interaction region that you're trying to describe, you'll get the same equations of motion. But now let's think about operations on the fields which don't change the equations of motion. And such operations will be called symmetries. So let's assume that we start with a Lagrangian, and the Lagrangian is such that if I make some mathematical transformation of the fields from phi to phi prime, that the equations of motion don't change, well, then the physics will be invariant under that operation because the equations are invariant. And that's a situation in which we say that we have a symmetry of the physics, because all of the physics is contained in the Lagrangian. I should say that this Lagrangian that we're writing down here is just the equation that we were talking about, the Klein-Gordon equation in this case, is the equation for a free field. So it doesn't actually contain much physics yet. To get physics, we have to add terms to this Lagrangian, which could be, we could add more fields, and then we could add terms in the potential, which mix the fields together. So for example, we could have added a field phi tilde and write down a term which is phi tilde squared times psi squared, for example. And that would actually correspond to an interaction term between these two fields, and subsequently between the two types of particles. Or I could have added, just with a single field, a self interaction. So in this example, I might consider adding phi cubed or phi to the fourth, or even some higher power of phi. And that would correspond to self interactions of phi particles with themselves. And so when we were for example, drawing a diagram like this, this diagram arises because the Lagrangian contains some terms which are schematically of the type E minus A E plus, just schematically, where A would be the field representing the photon, and so these are all fields. So this is why the Lagrangians are important, because we actually read off from the Lagrangian itself these interaction rules, if you like. And if I put here some constant lambda, then this lambda actually appears as part of the Feynman diagram. And big lambda corresponds to strong interactions, and small lambda corresponds to weak interactions. In this particular diagram, lambda is in fact the electric charge which in natural units is just a number. So this is just to put give some further background as to why we're interested in understanding Lagrangian field theories. In fact, this particular Lagrangian field theory we're talking about, that's on this page, is the Lagrangian for quantum electrodynamics. Well, here I've included not just electrons, but muons. And this is the most precisely, this is the part of the standard model Lagrangian with which you can do the most precise calculations, and these are some of the most precise calculations of any mathematical model in the history of humans that has been tested against experiments. Okay, so next time we'll continue with symmetries. What we're going to show is that that there's a way to compute what the conserved quantities are, and for the Lagrangian for the Klein-Gordon field, or in fact complex Klein-Gordon field, we will see that the conserved, the complex Klein-Gordon field has a symmetry, which is a U1 symmetry, and if the field has charge Q, then the Lagrangian is invariant under this change of phase of phi. And then the Noether's theorem tells us that there's a conserved quantity, a conserved 4 vector, and that 4 vector is exactly the 4 vector that we derived from the equations of motion before. Which means that the interpretation we were giving before is in fact, in terms of putting the charge in front of the current and so on, is in fact correct. stop. So I'll take any questions about today's lecture. We'll go through I think I was a bit too quick with this Lagrangian manipulations. We'll go through it again carefully next time. We need it for Noether's theorem anyway. What did we do before? This thing, I think, straightforward. So are there any questions?